Hello everyone. Today we are going for the data analytics course, and the topic that I'm going to take today is the support vector machine. And myself, Dr. Anju Mishra, I'm associate professor in the Department of Information Technology, Akgec Engineering College, Ghaziabad. So support vector machines, or simply we say that SVM is one of the most popular algorithm that we used, and this is a kind of supervised learning algorithm. So supervised means that it uses the labels to identify the types of pattern that needs to be classified or regressed. And the use for this algorithm is in both for the classification problems as well as for the regression problems. Primarily, it is used for classification problems in machine learning. So SVMs are adaptable and efficient to a different variety of applications, and it can manage high dimensional as well as nonlinear relationship, and it can discover these nonlinear relationships from the data. The goal of the SVM algorithm is to create the best line or decision boundary. So the goal of the algorithm is to create the best line or the decision boundary that can segregate n-dimensional space into different classes that we are having. And the points which belong to the data set that can be categorized into the different categories by using a separating hyperplane. The hyperplane is a line that separates different data points into the space into multiple categories or the classes that have been already given with the data set. And the algorithm tries to find the margin between the closest point of different classes, and it keeps this margin as maximum as it is possible for the given data set. The dimension of the hyperplane depends upon the number of features. If the number of input features is 2, then we can separate this type of two-dimensional data by using a single line. If the number of features is increasing, so for example, if we are having the input features as 3, then how we can separate this data into a three-dimensional space. So the dimension for the plane or the hyperplane will become a 2D plane. So by using a 2D plane, we will be able to separate out different types of classes from this given three-dimensional data. It becomes very difficult to imagine when the number of feature exceeds 3. So from the visualization point of view, as humans, we can only we are only comfortable with the three-dimensional data. Beyond that, we are not able to perceive the kind of data distribution into the higher dimensional space. Now SVM chooses the extreme points or the vectors for creating the hyperplane, and how it chooses the support vectors to create the hyperplane or the boundary. So for that, it uses the concept of distance, and it measures the distance between the different points of different classes that are closer enough. So so it can use a Euclidean, for example, distance measure to find out the distance between the closest points of two classes, and all those points will be treated as the support vectors, and these support vectors will be further used to find out the decision boundary that is cutting down the whole space into two portions. If the problem is to classify two different classes into the two-dimensional space, and that way we are finding out a hyperplane that is classifying the data into two separate categories. So in this figure, you can see that we are having points belonging to two different categories. So we are having some green points, then we are having some violet points, and the support vectors are these. So this is one support vector, and this is another support vector that we can see here, and these are closest points to the other class points, and these will be used to create the hyperplane or the decision boundary here. So you can see that how we are finding out the hyperplane. So we can create or we can draw a separating line here, a 1D line that you can put here, that is separating these two class points. But here the problem is that infinite number of such lines can be drawn within these this space, and we need to find out the maximum margin hyperplane or maximum margin line out of all these lines, so that we are having a decision boundary, a good decision boundary, which will be used for the future points which we have not seen yet. So this is how the support vector machine algorithm works for the data. So since it is a supervised learning algorithm, you are giving your model certain observations. These could be kind of a set of pictures of different animals, and when these observations are going to the model, along with these observations, we are also passing the label or the class type of these animals. So for the cats, we are, for example, passing the label as the cat, and for dog we are passing the label, for example, as a dog. And then the model is going to be trained, and the model is predicting then the outcome for the new data which it has not seen previously. So once your model is learned, or it is able to find out the decision boundary or the hyperplane, then if you provide the new data to the model is able to predict the class label for that particular input pattern. This is the problem of the classification. So as you can see that when we are passing it a picture of a new cat, then your SVM algorithm or the model is able to predict that it is a cat. Now, there are two types of SVMs that we mostly use. One is called as the linear SVM, and the other type is called as the non-linear SVM. So, in the linear SVM, we use the data which is linearly separable, and a data set which can be classified into two classes by just drawing a line between the two classes is called a linearly separable data. So if your data is having a linear relationship, or it can be linearly separated, then the SVM classifier, the type of SVM classifier that we are going to use is the linear SVM or the linear support vector machine classifier. So this is one example of the linearly separable data. As you can see that points are distant enough here in the space, so that we can easily separate these 2 points into 2 different portions into the 2D space. Now, for example, how this SVM algorithm is going to separate a linearly separable data. So when we talk about the working of the linearly separable data, as you can see that we can draw multiple linear lines here to separate out both of the categories here, and whenever a new point is coming, which is a future point, that also will be categorized into the correct category, the green one or the blue one, based upon your algorithm's hyperplane. Now, the SVM algorithm finds the best line, and this best line could be the one which is having the maximum margin out of all the other lines which are present, or which can be drawn into this separating area. And the closest points, as I already have told you, that the closest point here are treated as the support vectors. So in this case, as you can see, if I talk about with respect to this line or this boundary, then this point is closer to this line, so it can be treated as a support vector. Similarly, this point is closer enough to this line, so this red line, so this becomes another support vector belonging to the second category. And if we talk about this line, this slanting line here, again we can find out similarly the support vectors belonging to the different classes that we have in the data point. Now, there is a concept of the optimal hyperplane. So as you can see that optimal hyperplane is the hyperplane or the decision boundary that is having the maximum margin between the two classes. And why we need this maximum margin here? So the maximum margin hyperplane will be using to categorize effectively the future points that we have not yet seen, or the model not yet not have seen, right? So in future, if the person is giving giving another data point as the input, and it needs that the model should generate the corresponding category. For example, if we are giving it a picture of another kid which was not part of any picture that you have provided to the model for a cat, then for this unseen type of cat, the model should be able to clearly say that this is a picture of the cat. So if the maximum margin will be there in the in the decision space, then what we can do, that if a point lies here, for example, next time, then here this point will be again classified correctly to the corresponding decision boundary, or to the corresponding class. Now we talk about the non-linear SVM. So as you can see that linearly separable data, we are not having any mostly the issues, because data is all having a linear kind of relationship. So we can just need to draw a line that can separate these two classes from each other. Now sometimes the data is not linearly separable, right? So it is having some sort of non-linear relationships, and in such cases we cannot use a linear SVM algorithm to separate out the data points. So one example for non-linearly separable data is here as presented in the figure, and you can see that now the points are so distributed in the space that we cannot clearly separate them out with the help of a line, right? So this type of data is called as a non-linear data. Now for this type of classification problem, where your data is having non-linear relationship into the data set, then we need to use the non-linear SVM classifier to separate out these type of data points. Now how the non-linear SVM deals with the this type of problem when the data is not linearly separable. So in that case, what non-linear SVM algorithm does, that it uses the kernel trick, and kernel trick is the way to map the input data into the higher dimensional space. So so because of the kernel trick, the SVM algorithm does what, that it maps the input features into the higher dimensional space. So for example, if your input data is having 2D features or two-dimensional features, the kernel will be mapping that 2D feature into a three-dimensional space. So it is going to increase or add more dimension to your data, so that eventually it is going to be separable. So this phenomenon, or this type of adding more dimension to separate out the data is called as the kernel trick, and SVM uses the kernel trick. And as you can see here, that one more dimension, which is called as the Z dimension, is being added by the kernel here, and the data is mapped to now a three-dimensional space. So previously your data was in two-dimensional space, and now the data is in three-dimensional space. Now, so for example, if the given data is only having two dimensions x and y, now this data is non-linearly separable, so we cannot simply draw a hyperplane with dimension 1 here to separate out the data points. So the kernel function is mapping first this data into a higher dimensional space. And how the kernel function is doing that? So for calculating the third dimension called the Z dimension, it is actually using a function to finally find out the values for the third dimension. And once your point is having three coordinate values, one for each respective axis, then you can map that two-dimensional point into a three-dimensional space. And this is going to help us to discover the best hyperplane that is going to separate your data set into different categories with widest margin or the best margin. Now, since we are in a 3D space, hence it is looking like a plane parallel to the x-axis. So as you can see in this figure that once we are visualizing the data, the 2D data into a 3D, space, the features are elevated, towards the upper, direction. So as you can see now, your blue points, they are, kind of aggregated into the upward portion of your space, and all the green points, they are, segregated down. And this way we can find out the position of the hyperplane as here. And again, multiple such lines or multiple such hyperplanes, the two-dimensional ones in this case, we can find out. So basically it is a kind of surface that we can now draw to separate out the upward, portions and the downward portion of this, three-dimensional space. And out of that, whatever, hyperplane or whatever, decision boundary or the surface is having the maximum margin between the points of these two classes, that will be, considered as the best hyperplane. We also can, visualize the same data in the figure, shown here. So as you can see that if you are converting back this data from 3D to 2D, we are, getting a segregation like this. So we can visualize it like this on a 2D plane. And as you can see that when you are, setting up z is equal to 1, which is the third dimension, then you will be getting a circle with a radius of 1 in this case. So this is another example of how the nonlinear SVM, works. And here you can see that we are having a one-dimensional data set with us. And as we can see here now, because the data is one-dimensional and there are, certain blue points, and after that certain red points occurs, then after again, certain blue points comes, after that certain occurrences of the red points and then the blue points. So there are intermittent, presence of these red and blue points, and clearly we cannot, separate this type of data again with a linear, kind of decision boundary. So by, drawing a line, it is not possible to linearly separate these two, kinds of points in the space. So again, we can use a nonlinear, SVM classifier that can, elevate the dimension from 1 to 2. And once your data is mapped to the two-dimensional space, you are, going to see the separation of these red and blue points. And how it could be? So again, the kernel function you can, use to find out maybe the distance between these points from the origin. And how we are finding out the origin? So for example, we have drawn a line, here after these 5 blue points, and we are treating it as the origin. So you are, again, considering the same, point now into a two-dimensional space, and now you are drawing these points with respect to the distance of from the origin, right? So maybe like the curve goes like this. So when you are mapping in this way, maybe the red points, those are, lying here, and all the blue points are going upward. So that way, when we visualize, we can now check that if the data is, mapped to the, two-dimensional space, now it is easier to find out a hyperplane or a boundary that can, separate these data points from each other. Now there is one more scenario. What happens if we are having a data set where, the two, where the data is linearly, separable, but there are certain, outliers that exist in the data, and due to those outliers, we are not able to find out a perfect boundary or the hyperplane that can separate out these, points. So now, whatever I use, for example, if I normally look at this type of data, I can see that, there is a sufficient margin between the two classes, but because of this one outlier point, I'm not able to, find out the, the perfect hyperplane that is separating. So for example, even if, I am, for example, using a line here, for example, okay, this line is not going to, represent a perfect, boundary or a perfect classification because of this particular point, right? So because of this outlier point, why we are calling it a outlier point? Because as we can see that the distance between the other points of blue type and between this blue point is very, very large, right? So this is a outlier point, and even though we can separate out most of the points by just creating a one dimensional hyperplane here, but not all the points, right? So one of the important feature or the aspect of SVM algorithm is that it is robust for the outliers, of the presence of the outliers, and how this treats the data when it is having the outlier. So in that case, the algorithm is trying to find out the hyperplane as usual, and once there are outlier points, so for every misclassification of these outlier points, a certain kind of penalty. Okay, so this penalty P is going to be associated for every misclassification of a certain point, right? And the motive of the SVM algorithm is to minimize over this penalty. So whatever hyperplane we are going to draw, whichever is having less penalty in this space in terms of these outlier points, that hyperplane will be considered for the final decision boundary. And this is the way how the outlier case is going to be treated up. So this we already have covered. Now we are going to see some of the application areas. So some of the application areas where we can use the support vector machine algorithm are text classification, use SVM for image classification, we can use them for spam detection, we can do the handwriting identification using SVM machines, and using the SVM we can also do the gene expression analysis. Face detection is another common application that uses the SVM algorithm, and anomaly detection is the application that again uses the SVM algorithm. Now, what are the advantages of SVM algorithm? So first, it is effective in high dimensional cases. So if your data is having a lot of features, so the size of the data set is quite low, but it is having higher number of dimensions or the features, then SVM is the best algorithm that needs to be used in that case. And its memory is efficient as it uses a subset of training points in the decision function called the support vectors. The third advantage is that different kernel functions we can use to specify the decision boundary or to find out the the hyperplane here in this case. Now there are certain terms that we need to know about the support vector machines. So hyperplane is nothing but a line or the decision boundary that segregates the classes or the data set or the data points into multiple classes in n-dimensional space. And we need to find out the best decision boundary out of all those boundaries or the lines that we can draw to separate these two classes or more than two classes, right? This best boundary is known as the hyperplane of the SVM. The dimension of the hyperplane depends on the number of features that we are using. So for example, in your data set, if you are using 2 features, then the dimension of the hyperplane will be 1. If you are using 3-dimensional data, then the hyperplane dimension will be 2. So always we are having k-1 dimensions for the hyperplane. So if your data is having k dimensions, then the hyperplane dimension will be equal to k-1 always. So this is the characteristics of the hyperplane. And maximum margin hyperplane, as I already have told you, that is the hyperplane that that divides the classes with the optimum margin or optimum distance. Now the concept of margin, so margin could be of 2 types. It could be a soft margin or it could be a hard margin. The hard margin is the margin that clearly separate out all the categories or the classes that are present into your data set, and there are no misclassification rates here. So that type of hyperplane that perfectly divides the classes separately, that is called as a hard margin. But when there are outliers, the hard margin is not the the successful approach to use. So in that case, the SVM algorithm uses the concept of the soft margin. So soft margin is a margin that is separating out most of the point of a given category from the other category points, but there are presence of certain outlier points. So because of that, it is not a the best or the optimum hyperplane. So even though it is it can be used to separate out the points successfully, and there are certain outlier points that that are not perfectly classified by using a soft margin. Now there are certain measures that are attached to the support vectors. So C is a parameter or a regularization parameter that can handle the margin maximization and misclassification fines, and the penalty for going over the margin or misclassification of data items is decided by the C parameter. A stricter penalty is imposed if with a greater value of C. So if your C is having greater value in the result, the penalty figure will be more, and if the value for C is less, then a smaller margin is there. So it is giving you kind of less penalty for these misclassification points. Another parameter that is used in the SVM algorithm is the Hinge loss. So Hinge loss is a loss function in SVM, and it punishes or used to punish the incorrect classifications or margin violations. And the objective function is SVM algorithm is to frequently formed by combining it with the regularization term. So what we are going to do, that we are combining the regularization term C and this Hinge loss together to optimize the SVM algorithm. With this, I end up here. Thank you so much.